afternoon, everyone. My name is Gemma, and I would like to be judged. So this is some work that I've been doing with my advisor from the University of Washington, Eric Stein, in collaboration with Luke Parsons and Greg Hatham. And I'm going to be talking about reconstructing winds around Antarctica using data assimilation.
Just give it a word.
So the talks this morning introduced the importance of westerly winds pretty well, but just to reiterate, westerly winds are important because of ventilation of carbon dioxide from the ocean. They modify ocean circulation in a way that the ice sheet can sense. A common way of measuring westerly wind belt activity around Antarctica is with the Southern Annular Mode Index, or the SAM Index, which is the pressure difference between mid and high latitudes around Antarctica. So this plot on the right is showing the station-based SAM Index that we have available starting in 1957, and you can see that there is a bit of a positive trend here, meaning that this westerly wind belt is starting to contract around Antarctica. The westerly winds are also important in the Amundsen Sea, as Andrew gave a good introduction to this morning. So variability in sea level pressure in the Amundsen Sea causes winds to change at the continental shelf break. So this is the continental shelf break. These are the Amundsen Sea ice shelves, and the water, or the colors here, are showing the thickness of circumpolar deep water. And the theory here is that as winds are blowing from west to east, meaning a westerly wind, there's more uplying of circumpolar deep water coming onto the continental shelf and intruding all the way to the bottom of the ice shelves where it's melting the ice from below. So during periods of stronger westerly wind, we get more melting. So this leads to the hypothesis that since the ice shelves in the Amundsen Sea are melting now, the winds have probably become more westerly in recent decades. But we currently don't have the data available to support this hypothesis, since reliable wind data starts in 1979. So plotted here are ERA interim winds, the zonal wind anomaly. So a more positive zonal wind anomaly means a more westerly wind. So based on what we know, we would expect to see a positive trend, meaning that the winds are becoming more westerly in recent decades. But you can see we don't have much data here to find any sort of discernible trend. So a longer record of westerly wind activity around Antarctica could be really useful in answering questions like this. So I propose that we can use data assimilation to produce longer records of wind reconstructions using proxy data. So we can use the proxy database in data assimilation. And these are great because they are longer than the instrumental record, though they do represent individual locations. They're pretty sparsely distributed, and they're mostly temperature-dependent proxies, so it's not immediately obvious how to get to winds from these records. We can also use climate models, which are great because they're spatially complete, and they simulate multiple climate variables, including winds, but they're not constrained by observations. So with data assimilation, we can combine the advantages of both of these. We do this using a Bayesian approach. For those of you that are familiar with data assimilation, we use the ensemble Kalman filter. And with this method, there's uncertainty built into the method, so we're left with a distribution of states. And we also get fully gridded reconstructions of multiple climate variables with this method. Sorry, these bugs are terrible. So a couple notes on the method that I use. We can use any climate model as what we call the prior state. So this is our initial guess before we simulate the data. So this is a word that I'll be using throughout the talk is the prior, so I'm referring to the climate model that I'm using to start my data simulation. We also use an offline data simulation method, meaning that for every year that we're reconstructing, we use the same initial guess. So it's a flat line, so when you look at any time series of reconstructions, all of the variance is coming from the proxy records. It's also important to note that proxies have influence when they're assimilated if they're significantly correlated with climate at the reconstruction site. So for reconstructing winds in the Amundsen Sea, which is shown by that white star, all of these proxy records that are in the red or blue region means it is correlated pretty well with Amundsen Sea winds. So for example, there's a strong tropical Pacific teleconnection, so these corals that are in this region will get a lot of influence in trying to reconstruct winds here. So on to my reconstructions. As a first pass, I want to see how well we can do at reconstructing temperature. So shown here are 3 reconstructions from 3 different priors, meaning 3 different climate models. And plotted are the temperature trends from 1957 to 2000, because we're all familiar with this. And we do see that regardless of the prior we choose, we see this West Antarctic warming trend that we're all familiar with, demonstrating that this method does pretty well at reconstructing temperature trends. So I can also reconstruct pressure with this method and reproduce the SAM index. So this is 20th century SAM index. My reconstruction is shown in blue. On the left is with 20 CR as the prior, and on the right is with PACE as the prior. And they both do extremely well when verifying it with the Marshall SAM index, shown in green, which is the station-based index, as well as verifying it with the Abram SAM index, which is shown in orange, which is based on ice core analysis completely independently from our method. So this is just an example of two reconstructions from two different priors, but we also get very good results when I use different priors as well. So on to the wind trends. To see how well we can do at reconstructing winds at the Antarctic level, I can verify it with ERA interim wind trends. So this is from ERA, the wind trend from 1979 to 2000, and all this red here means that the temperature, or the wind trends are becoming more westerly. So I can compare my reconstructions with that ERA trend. So this is from 6 different climate models as my prior, and we see a very similar result regardless of prior that we use that all show the strengthening of the westerly wind belt. And I can do this reconstruction by simulating all of the ice, or all of the proxies in my database, including ice cores and tree rings, or I can do it with just ice cores, and I get a very similar result when I just use ice cores, showing that the signal is mostly coming from the ice cores, which is nice to see. So on to the winds in just the Amundsen Sea. So now I'm averaging my reconstructions in this little box here at the continental shelf of the Amundsen Sea. And again, in blue is my reconstruction. So here I'm using PACE as the prior, and I'm assimilating all of the proxy records, including ice cores and tree rings and coral records. So the internal variability looks pretty good when comparing with the ERA interim, which is shown in orange. You get a correlation of about 0.4, which is very good. And again, the positive wind anomaly is showing more westerly winds. So just to see how it does with another prior, this is with ICSM last millennium as the prior. We again see very good correlations with it, but a few differences in the trends and amplitudes. So we get a little bit more variable reconstructions with different priors here. Something interesting that I found is that if I do these reconstructions and just assimilate the corals, these correlations with the ERA interim improve even more. So the corals are doing very well at reconstructing winds in this region. So I can also compare my results to the work from Holland et al. Published just this year. So that is shown in gray here. They modeled the winds in the Amundsen Sea from 1920 to 2000 and something. And they found there was a significant trend of 0.5 meters per second per century, which doesn't sound like a whole lot, but it was a significant trend. So this is currently the best standing estimate of 20th century winds that we have in the Amundsen Sea, so it's something that I can compare my results to, recognizing that this is a model and it does come with some uncertainty. Oh, and Eric Seig will be talking about this tomorrow, so you can ask him more about it. So comparing my results to the Holland work, my results are shown in blue, and Holland work is shown in green, or gray here. So this is from 1920 to 2005. You see there's pretty good interannual variability agreement, especially starting in 1950 and onwards. The correlation is 0.6, which is excellent. The trend in my reconstruction is only 0.1, so it doesn't really support our hypothesis that winds are becoming more westerly. So if I use the same PACE prior, but I only assimilate the coral records, I get even better correlation with Holland, and I get this positive trend of 0.5 meters per second per century, which we expected to see. So I get some variable results based on the prior that I choose and the proxies that I assimilate. So this is a work in progress, figuring out which reconstructions do the best job. But we do have reason to believe that this PACE corals only run could be the best estimate. It verifies well with both the ERA interim and with the Holland work. The PACE model is tuned to tropical Pacific SSTs, instrumental SSTs, which eliminates a lot of biases that a lot of other climate models have in the tropical Pacific and in the Amundsen Sea. There's reason to trust that model. And we know that there's a strong teleconnection between tropical Pacific and the Amundsen Sea climate, which is a reason to trust that the corals are capturing Amundsen Sea activity. Some concluding remarks. We can use this method to reconstruct Antarctic temperature trends and westerly wind belt trends in recent decades, regardless of the prior that we use. We see the same good agreement of 20th century SAM index, also reproducible regardless of the prior we choose. Most of the signal on these scales come from the ice cores, and when we we look at the smaller picture at Amundsen Sea wind reconstructions, we get a little bit more uncertainty where the results are variable based on the prior and the proxies, but they do a decent job at reconstructing winds with some of those combinations. And they sometimes support the columns at all work, but this is a work in progress. Thank you.
Perfect timing. We maybe have time for a question or two while we switch topics. Ted?
Well, I kind of wanted to put the slide up just before your conclusions. I was going to ask you about the graphic on the left here. It looks like there's only one break point there right around 1951. And if you were to subtract a half a meter from the earlier record, you'd have a very high correlation both on the short term and the long term. And what struck me about these two graphics is that you've got a nice R value, but that's because the long-term trend is well represented, but it looks like the one on the left does a better job of capturing short-term variations. Okay. We can talk offline.
Okay, yeah, what do you mean by short-term variation?
Well, all the little spikes in there are better tracked by the one on the left since 1950. Well, since 1950.
All of the same
And if you were to subtract a half a meter from things before 1950, again, you'd see pretty good tracking of all those spikes. We can talk offline.
Okay.
Let's have the next speaker come up while we answer one question. Over there, right?
Given that the corals produced your best runs, I was wondering if it was possible maybe to go back further in time, because there are several coral records that go back multiple centuries rather than just to 1920 now that you've verified it.
Yeah, absolutely. We definitely could. I just sort of focused on this because we have a model to compare it to in the 20th century. And as we go farther back in time, it gets a little trickier because there are fewer proxy records, but it's absolutely something we could do.
All right, thank you, Gemma. Our next talk is going to be by Michelle Maclennan from University of Colorado, talking about snowfall on Thwaites Glacier.
All right, hi everyone. My name is Michelle Maclennan, and I'm an undergraduate student at the University of Colorado. And today I'm going to be talking to you about the atmospheric drivers of snowfall on Thwaites Glacier. And we're going to start by looking at the surface mass balance. So on Thwaites Glacier, the surface mass balance is equal to accumulation minus discharge. And because accumulation is equivalent to snowfall almost, we can say that snowfall becomes the dominant contributor to SMB. But so this enables snowfall to buffer mass loss on Thwaites. But we don't necessarily have observations of snowfall below 900 meters above sea level. And so in order to study this, we need to rely on some climate models. So I'll be using RACMO2 and MERA2 to look at snowfall on Thwaites. So there are three ingredients we need in the recipe for snowfall. First of all, we need proximity to the coast, and we need steep surface topography. And Thwaites Glacier has both of these because the glacier slopes upwards steeply as we move away from the coastline to the interior. The third element we need is atmospheric flow orthogonal to the topography of the glacier. Now, in the mean on Thwaites, katabatic winds dominate. We have a strong outflow from Pine Island Glacier, which means that most of the winds, again in the mean, are coming down Thwaites Glacier, and there isn't necessarily any orographic lifting. There's also little seasonal variation in this, except if we look at the winds during high snowfall events. And what we see, if we look at the mean wind speed and direction during the times of high snowfall events, is a much stronger meridional flow from the Southern Ocean into the Amundsen Sea embayment and up onto Thwaites Glacier. So we want to know what's causing this, what's happening when the winds change during high snowfall events, and what's driving surface mass balance on Thwaites. So the main atmospheric component of circulation near Thwaites is the Amundsen Sea low, which is the system of low pressure systems just north of the Amundsen Sea embayment. Now this is also known as the polar variability because in the mean, if we look at the climatology of surface pressure, the Amundsen Sea low migrates zonally over the course of 1 year. So in the early months, so summer, in January and February, the center of the low is located mostly north and northeast of the Amundsen Sea embayment. But over the course of the year, the center of the low, again in the mean, migrates westward, almost towards the Ross Sea. And then around June or around midwinter, it ends up migrating back eastward again. So why does this matter? Well, it matters because the circulation around the Amundsen Sea low influences circulation up onto Thwaites Glacier. And if we have clockwise circulation about this low pressure system, we'll know that east of the low pressure system, winds will be coming meridionally from the north to the south, channeled into the Amundsen Sea embayment from the Southern Ocean. And when the Amundsen Sea low is located north and northeast of the Amundsen Sea embayment, we have less air channeled into the embayment and onto Thwaites, and more channeled zonally or even away from the embayment. So we can look at how this affects the climatology of snowfall on Thwaites. So if we take the monthly averages of snowfall at 5 different elevations on the glacier from a period of 1980 to 2015, we see 2 distinct features. First of all, there's much more snowfall at the lower elevations on Thwaites than at the higher elevations. So we see more snowfall close to the coast and less as we move towards the interior. The other feature we see is that there's distinct seasonality to the snowfall on Thwaites as well. So we see much higher snowfall in the fall, winter, and spring seasons than we do in the summertime. And how does this connect to the Amundsen Sea low? Well, if we remember, in those fall, winter, and spring seasons, the mean position of the Amundsen Sea low is located west of the Amundsen Sea embayment, which allows air to be channeled into the embayment from the eastward side. But then if we look in the summertime, when the position of the low is mainly north and northeast of the embayment, we get less air channeled in and thus less precipitation on Thwaites. So in order to look at the atmospheric drivers of snowfall events more closely, we can look at a time series of snowfall on Thwaites ice shelf and select certain snowfall events that we want to study. So I'm using these 2 models, RACMO2 and MERA2, so that we can compare a little bit how the regional model works in comparison to the global reanalysis. And I have time series for snowfall averaged over the ice shelf in the 1980 to 2015 period. And from that time series, we want to select snowfall events to study. So if we take the normalized accumulation of snowfall from both of these time series over Thwaites ice shelf, we see that they represent snowfall pretty similarly, especially when we get towards high snowfall events. Now in selecting snowfall events, we want to look at ones that contribute significantly to the surface mass balance of Thwaites. And if we take just the top 10% highest snowfall events in both time series, we find that these contribute to about 50% of the surface mass balance on Thwaites during that time. So these are the events that we want to study. Well, the next question is, when did these snowfall events fall? And as we expected from our snowfall climatology, most of the marked high snowfall events are occurring in the fall, winter, and spring seasons, with much fewer occurring in the summer months. And we also noticed that the distribution by season is pretty similar between RACMO and MERA2. So now we can use MERA2 to look at the large-scale atmospheric conditions that are occurring during these snowfall events. So we can start by looking at surface pressure, and I've split this up by snowfall events for each season. So if we look at the seasonal means of surface pressure, in all 3 seasons, we see distinctly the positioning of the Amundsen Sea low west of the Amundsen Sea embayment. But if we look at the surface pressure anomaly, what we also see is this distinct region of anomalously high pressure east of the Amundsen Sea embayment, or a blocking high over the Drake Passage. And the counterclockwise circulation about this high would also serve to drive air from lower latitudes directly into the Amundsen Sea embayment in conjunction with the Amundsen Sea low. What we see also is that there are differences in our surface pressure anomaly among the 3 seasons. So in the winter, we see the highest signal of this anomalous high pressure. And in the spring, we also see a distinctly anomalously low Amundsen Sea low. Now this signal is also represented in our temperature plots. If we take the mean temperature during high snowfall events for each season and the temperature anomaly, and what we find again is that in all 3 seasons, we get much anomalously warm temperatures over Thwaites Glacier. So what does this tell us? Well, this tells us that there are strong seasonal differences in the mechanisms for high snowfall over Thwaites. But if we sum our number of high snowfall events that were selected for each year, there's also a large interannual variability in the number of high snowfall events. So this is an ongoing project, and the next steps are to look at the large-scale atmospheric patterns and connect this to the southern annular mode and tropical Pacific forcing to see if we can find a link between these large-scale patterns that are happening in the Pacific and the local patterns of snowfall over Thwaites. Thank you.
Any questions? All right, well, maybe we'll move on and we can circle back to this during the discussion. We'll look up a few minutes. All right, so the last talk for this session is by Brooke Medley from NASA Goddard, and she's going to go a little deeper down into the fern.
Thanks, Matt. I'm going to talk today about everybody's favorite word, fern. It is important, and yet we often like to overlook it, and I feel like every time I come here, I'm always like, remember about the fern. Okay, so my question today is, will the pore space save us? So I'm at Goddard, lots of helpers, and all of this work is really in support of ISAT-2, our fantastic satellite that just launched last year. So fern, as you know, it has airspace, which is good because it can absorb water. And so on the left here, we have a healthy fern column. Basically there's no meltwater, and the meltwater can be stored sort of within the fern and be basically buffered from running off. On the right, when you start to get a lot more melt, you get less snowfall, then your pore space all fills up and you're kind of out of luck. And your ice shelf might collapse. But that's not going to happen. I'm giving it away. So fern air depletion, as I said, can increase meltwater runoff, which adds more to sea level and increases our chance of hydrofracture. So it's really important that we understand basically the current state, the health of the fern column, but also how it's changing. So and I should start with this caveat of we see these amazing images of water falling off, and I'm going to be living mainly in ideal model space where we have not necessarily representation of all the adequate processes. So just bear with me a little bit about that, but I do understand that this is a much more complicated problem than I'm necessarily presenting. So can we summarize sort of these processes in sort of a simple metric? And this is nothing new, this is done already, but I'm kind of showing off some new toys that I have. So the first one is what I call the Mera-2 hybrid. So thanks to Michelle for actually bringing up Mera-2. It's a global reanalysis product. We actually have a 12.5 kilometer Mera-2 replay that was only run for 15 years, 2000 to 2014. And so we actually use this in combination with the full time series, the Mera-2, which is about, depending on where you are, it's about 40 kilometer resolution. So not necessarily ideal, but to generate this hybrid product to get a much better spatial picture of precipitation, and melt and temperature. So please contact me if you want to look at it or use it, not just look at it. And the unfortunate thing about MERA 2 is that they did not output melt, which is a total bummer because that's really what we want if we're running a firm model. And so we instead made a really simple degree day model. Bear with me. I know that sounds scary and wrong, but it actually worked out really well. And we calibrated it against Luke Trussel's QSCAT melt reads. So how does this compare with RACMO? I feel like Michelle was a perfect intro for me. So these are just total snowfall amounts over the ice shelves. And so Antarctic ice sheet, East Antarctica, West Antarctica, Peninsula, Amundsen Sea embayment. And so on the left is your net accumulation. On the right is meltwater production. And so you see that they actually match very well. And I want to remind us that we are not Greenland yet. So snowfall is 450 gigatons per year. Melt is only 70 gigatons per year. So we haven't approached Greenland numbers yet by any means. So we're going to do a really simple calculation, division, to figure out how vulnerable the fern columns are. Basically, you take the liquid water amount and then divide it by the salt. And so if you get a vulnerability index of 0, there's no melt. So it's dry, healthy, lots of pore space. If it's 1, that means all of your snowfall is melting, so it cannot support a fern column. And so somewhere in between is this sort of gray zone of, as you're starting to approach 1, when you start to get meltwater accumulating and running off. Obviously, it's much more complicated, as you can see from this figure, but it's sort of this general idea of what's going on. So here's that index. Whether you use MERA 2 or RACMO, you get pretty much the same exact story. It's very yellow over the big ice shelves, and then once you move towards the peninsula, you start to see reds, but it's also very red in East Antarctica. And for this meeting, it's very boring in West Antarctica. It's very healthy fern. It gets a lot of snow there, which is good. I have good news for us. I might be the first person. So is this actually a good index? And so what I'm going to use here is to actually use fern model simulations of the actual pore space to compare it with the vulnerability index, just to give us an idea of, is this somewhat reasonable? And so in support of ISAT 2, we created this GSFC FDM, which is a fully Antarctic-wide and Greenland simulation of fern properties from 1980 to 2019. And it uses the community fern model. And this is also available if anyone wants to contact me. And so if you compare the mean fern air content that you get over every individual ice shelf with this vulnerability index, not surprisingly, yes, it is a pretty good indicator. And as you can see, some of the shelves are approaching around, above 0.5, and they have fern air contents below 10 meters of fern air. So should we be concerned? I mean, what are we seeing? Well, waste shelves are doing fantastic. It gets a lot of snowfall, and so all the colored dots here represent your favorite West Antarctic ice shelf. And so they're some of the most, have some of the most pore space of any ice shelf. So not particularly exciting, but as you start to see what are the ones that are vulnerable, obviously the peninsula, Larsen Sea, Georgia 6, obviously, I'm speaking only from an atmospheric standpoint here. There's other reasons why an ice shelf might collapse, obviously, but from an atmospheric standpoint, these are the ones that are doing, I guess, the poorest. And there's lots of East Antarctic ones as well. So West Antarctica is really this sort of, we get so much snowfall and so little melt, there's a lot of pore space. And this is just comparing the two models, MERA 2 and RACMO, and just to show you the results don't change. And so, this is boring. So the question is this evolving? Because that's kind of the key important question. So if we look at meltwater production from 1980 to present, this is for all of Antarctica, I should say all of Antarctic ice shelves. This is Luke's QSCAT data. Ooh, I hope you can see that. I don't mean to blind you. this is RACMO. This is just meltwater production. And then this is the degree day model that we put together. And they actually match very, very well. And even if you break it down on shelf by shelf basis, it still does really well. So what you can note is actually meltwater has been declining, at least according to these two models, since 1980. But I'll be the first to say there's a lot of interannual variability here, so I wouldn't necessarily trust that anyway. But there's no increase and potentially a decrease. And then this is just breaking it out by, hey, here's West Antarctic ice shelves. And here's Amundsen Sea embayment, if you only care about that. But the story is pretty much the same around all of Antarctica, actually. So models suggest a decrease, actually, in the vulnerability index over the satellite era. But again, take that with a grain of salt because it's a very short record and a lot of variability. And I should note, because the vulnerability index isn't just melt, it's also snowfall. And so Mera-2 actually has some significant gains in snowfall, whereas RACMO pretty much is flatline. So, summary. The waste shelves are the most stable from an atmospheric perspective. And then several East Antarctic and Peninsula shelves are approaching Larsen AB numbers. Meltwater production appears to have decreased. Strong caveat there. But that interannual variability makes it really hard to kind of say with any level of confidence if that's truly a trend or just the fact that we have a very short record. And then I kind of want to side note here. This is from Jan Lennertz. This is CSM2. This is the water balance is the same thing as the vulnerability index, and it's probably really hard for everyone to see, so I'll just describe it. CSM actually shows that the vulnerability index should be increasing basically over the same time interval that we see. So there's been a strong increase in melt in CSM2 over the same time interval that this analysis is through. So there's this sort of, we need some reconciliation here between these different models where why does one show we should be seeing increase in melt, and the other actually shows a decrease. So there's this inconsistency, or at least we need to be able to understand why there is this inconsistency. So again, we all know this, we expect more melt in the future. It's not what we're seeing, at least in the two models I'm looking at. So I would say the jury's a little bit still out. I think we need to make sure that we can understand why the melt is decreasing, if it's decreasing, and what the different models actually, or why the different models actually show sort of opposite results effectively. So there's, by no means there's a ton of more stuff to do. So anyway, that's all I have. And I will just finish up with, please contact me if you're interested in any of this data. It's 20 terabytes of Fern, so I know that excites everyone. So please let me know if you want to use it. Thank you so much.
Any questions for Brooke? Yeah, in the back. Is that Matt?
Matt.
I'll wait for the microphone. Set a good example for
And I'll invite our other two speakers to mosey on up here while we answer a few questions.
So this is a little bit of insider baseball, I guess, but you were validating your vulnerability index against a regional climate model, or against your Fern simulations, the Goddard Fern densification model. But doesn't the Goddard Fern densification model need to be driven by a regional climate model? Isn't this a little circular?
So it's entirely circular. So I just wanted to show, so the Fern model is forced by Mera-2, which is not, well, it's not a regional climate model, but it's by the atmospheric model. So of course, yes, it's circular, but there's also a temperature factor in there, and there's other things that control the pore space volume. So I was basically just trying to show, hey, you don't need a sophisticated Fern model to necessarily tell you the same story effectively. So yes, the Fern model actually, it came into play here very little because I basically said you get the same results if you just use a simple metric.
Thank you.
Hello. So this is a question about the amount of precipitation. So from what I understand, a number of models, including RACMO, overrepresent precipitation as snowfall as opposed to as rain. So is that something that shows up in the Meritu hybrid, and is that a problem in Western Antarctica in particular?
That's a good question. I actually was unaware of this sort of, maybe it doesn't let it rain enough, it has too much snowfall. From all of my comparisons over West Antarctica, the models do a fantastic job of getting the snowfall amounts, but it very well could be they're getting the right for the wrong reason. So maybe there isn't enough rainfall. And clearly that would dramatically change your ratios because it affects both numbers.
Well, but in fact, I'm wondering, yeah. So if what was currently showing up as snowfall is showing up as rain instead, it would actually be more vulnerable than you're showing, right?
Yes. So if there should be less snowfall for rain, it should be more vulnerable.
Well, I'd like to kind of move on to our discussion format because we only have about 15 minutes. So if you have additional questions, you can kind of work it into a group question. So before we do that, let's thank all of our speakers one more time. So I'll open it up if anyone has any general questions they'd like to ask the panel on this broad topic of surface mass balance and atmospheric portioning.
I have my question for her. Is it Gemma?
Gemma.
Gemma. So are you familiar with the work from Hillebrand et al.? They looked at the delta C13 for planktonic foraminifera found from the inner part of the Amundsen Sea embayment. And they found that the values, I think, increased at around 1940. And they were suggesting that's an anthropogenic effect. You want to maybe with the westerlies being driven south and forcing more upwelling. Any comments on that?
Sorry, they found a more positive delta C13, which means increased temperatures. Is that what that means?
Increased presence of warm water, circumpolar deep water, onto the shell. Onto the shell. The inner shell, yeah.
And you want to know if that has an anthropogenic component?
Well, yeah, that was their conclusion about that. I'm just wondering about your perspective from the data you've generated.
Yeah, I guess sort of the only way to see if, as far as I know, if there's an anthropogenic component based on my results is if I can support modeled work that is forced by anthropogenic forcing, which is the model of the Holland et al. 2019 that I showed. So Eric will be talking about that tomorrow and making that connection to anthropogenic forcing. So if I can, in fact, support his results, then that would show that the reconstructions I present are most likely caused by anthropogenic forcing. So that would go in line with that.
Brooke, this is for you. I'm frankly terrified when I see the MRE ice shelf grounding line vulnerability. I'm sorry, as if we didn't have enough problems like this. So can you comment on the reliability of this? Is it really?
It's pretty consistent. I mean, both RACMO, excuse me, and Meritu both show the same thing where there's very low accumulation. It's kind of a double whammy where it gets a lot of melt and very low accumulation, and that's what makes it very susceptible to sort of meltwater ponding and everything. So I totally believe it.
And the location close to the grounding line,
yeah.
Trust it, we can trust that?
Yeah, I mean,
yeah.
The resolution obviously is going to be an issue because, I mean, RACMO is 27 kilometers and the Meritu run is 12 and a half. But there's a clear pattern in the actual melt. I'd say the pattern actually is driven more from the melt signal because it's really, that's where sort of Luke's, because it basically shows all the melt is kind of up there. And more snowfall towards the edge, which also helps as well. So I think it's definitely a real thing.
But we need to take transport into account, right?
Yeah, it refreezes on
well,
the vessel.
Yeah, but if it's already basically no firn and then it gets advected and then you put snowfall on it, I mean, it doesn't really it would be worse if it was the other way around. Do you know what I mean? Like if it got a lot of snowfall, or it'd be better, sorry, if it was the other way around, where you got a lot of snowfall, then it vected, and then at least there's still some residual snow there to absorb, but it's kind of the opposite problem where it melts it, and then it gets infected and has more snowfall. That makes sense? I don't know if I'm crazy.
Sorry, you're going to talk about Amory, I've got to speak up. I don't think you need to be worried about Amory. I mean, it's a 2.8 kilometer thick grounding line, and it's been, melt streams have been forming on it for like a quarter of a century or longer. And it's not thinning.
Yeah. No, I mean, it's...
So it's like one of the most imbalanced ice shelves. Well, okay.
That's why I'm
Three.
terrified.
So why are you terrified about
No.
it?
I mean, anything I can kind of activate that part, when all the ice sheet models did just, they don't care. They absolutely don't care about that part. Even in our spin-ups, we ignore it almost. Anything that can really trip this part would be really a game changer. But if you're saying this, that the thickness is such that you would need to hammer this for a long time, that's reassuring. I mean, as a modeler, I'm looking at this like, whoa. Because we had this with this MIP6, can we trigger any area of Antarctica? Can we trigger when we see instability? And we're trying to map out all these areas.
So if you worry about hydrofracture, I mean, you have to get all that meltwater all the way up to the very front of the ice shelf, and that's
No, I'm thinking weakening the grounding line. That's really what I'm worried about.
it's still a really small number compared to the other mass balance components on that ice shelf. So I will sleep tonight.
A couple of things. There were a couple of papers, Brooke, where we used passive microwave, active microwave. We got the melt season, and we got how much the fern reflects active microwave data, and set up the same kind of vulnerability index. And I'm pleased to say that the ones that we picked as being close on hydrofracture were the same ones you picked. But over several other projects, looking at how icebergs break apart and what really happened with the Larsen B and the Larsen A, to Helen's point, you really have to have an ice shelf that's on its last legs structurally for hydrofracture to be able to do that massive disintegration that we saw. And the Amory is well braced, basically, by Gillick Island is the first one I can think of, but there's the whole shear margin on either side is pretty firm. So yes, vulnerable, but there are many, many steps before you get to break up. And really, the only place that looks like it could break up but hasn't yet is the northern part of the Larsen Sea and the Wilkins Ice Shelf, which is sort of in the process of breaking up.
Yeah, I agree with everything you said, and it's really, there's an atmosphere component, there's an ice component, and there's an ocean component to this, and this is just purely the atmosphere. So I can say, I should have said atmospheric vulnerability index or something, but yeah, completely valid point, and we're just saying we can tell you about how the atmosphere impacts it, but obviously there's dynamics involved.
Thanks. This is a question back for Gemma. You showed us the time series of the zonal wind stress, but we often think about the interior density surfaces responding to the wind stress curl. So I wondered if you've looked at trends in the wind stress curl and whether you see the same sort of intensification, or if you see any trend whatsoever in the curl.
I guess I'm just hoping that the reconstructions where I focus in on the zonal winds at the continental shelf break will capture sort of that curl, because it'll capture sort of the transition point between the easterly winds coming off the continental shelf, or coming off the ice shelf, and the westerly winds coming outside the continental shelf. So I guess I'm hoping I'm capturing an increase in westerly winds as either the westerlies are increasing and the easterlies are staying the same, or the easterlies are increasing and the westerlies stay the same, which I think will the upline will feel. Does that sort of answer your question?
Well, if you have a gradient in the winds and you shift them, you'll see a change in the magnitude of the winds, but not a change in the wind gradient, which is the curl. Right. So if you see an intensification of the zonal wind stress, it doesn't necessarily mean that the Ekman pumping or the Ekman suction has changed. I guess that's the question I'm trying to get at.
Yeah, I'm not entirely sure. I guess wind stress is another climate state that I can reconstruct. So I've been showing zonal winds as opposed to wind stress.
Yeah.
I a while ago I looked at them and they looked pretty similar, looking at wind stress versus the zonal winds. Yeah, I don't know. I have to think more about that.
Yeah, we can chat about it after too.
Okay,
That'd be good. Thanks.
Yeah, I have a quick follow-up for you. Did you look at sea ice at all in terms of how that might affect wind stress as opposed to winds themselves?
No, I haven't. It's an interesting idea.
So for Michelle and Brooke, you're both saying it's dumping a ton of snow on Thwaites all year except the summer, I guess. Will the snowflakes save us? Like, so will that actually impact anything? Or how will it? Because it will.
Well, a few months ago, I averaged snowfall over Thwaites Glacier and Thwaites ice shelf separately over the time period for each year, and I saw different trends in the Run of Rackmo 2 that I'm using, which is at 5.5 kilometer resolution, and Mara 2, but they were really small trends over time, so I haven't seen any distinct trends in snowfall, but hopefully understanding the atmospheric conditions that lead to snowfall will give us a better idea of what that will.
Yeah, and I agree with what Michelle just said, and it's really the trends, right? I mean, Thwaites has been getting a lot of snowfall for a long time, but it's losing a ton of mass, and if we're seeing effectively no change in snowfall, that's not compensating anything. So right now, I wouldn't put my money on snowfall saving anything, but it also depends on what you mean, because you could also talk from a firm perspective as well, of like, will it absorb water? That's sort of a different look at it. But I mean, the rates at which Thwaites is losing mass, it's incomprehensible to think that snowfall could quadruple or something in 10 years or something. So no, I think it's unfortunately not keeping pace. Ask questions.
Sure.
Sorry, just one quick question for Gemma. Can you use other atmospheric variables in your reconstruction to sort of validate which one maybe does a better job? Because I think you were showing, like, depending on which initial state you used, you kind of get these different trends. And I don't know if you also reconstruct other atmospheric variables that you could then look at with other sort of independent data and try to make an assessment of the quality of the reconstruction. I'm not sure if that's possible.
What variables are you thinking of? I guess I checked temperature and pressure, and those did pretty well.
Right,
Do you have
and
any others?
snowfall or, yeah.
Snowfall is a little trickier. Yeah, it's something I can try to do that I think I'm even less confident I'll be able to do snowfall than wind. If you have any ideas, let me know.
Okay.
So I have another question relating to sea ice. So you mentioned that the sea ice would change the momentum transfer from the winds to the ocean, but wouldn't also the sea ice cover change the precipitation so that the same on-coast winds would pick up more moisture if the sea ice is close to the continent versus if you have a sea ice cover that's extending further out. So is there any systematic changes in sea ice in that area, and is it affecting the precipitation? That's the question to who may want to answer.
I'm happy excuse me, to take a stab at that. When it comes to sea ice and precipitation, it's really complicated because the question is the loss of sea ice driving the precipitation change on land, or is it just a change in atmospheric circulation that changes both the sea ice and increases precipitation on the coast? So it could be, you could misinterpret a relationship between a change in sea ice and what's happening on the land ice just because if it was simply driven by some sort of larger scale atmospheric process, whereas maybe it also maybe it's kind of a double whammy where the circulation shifts it and also contributes to more moisture into the atmosphere and then more deposition on the land. But this is actually kind of an ongoing and really complex sort of try to understand the actual linkages between what happens on sea ice and what it means for precipitation on land, because it's not just a simple correlation equals causation effectively. So it's really quite tricky, I would say.
Maybe one question for all of you, and that's these different processes you each described in some sense compensate each other. So you have increased ice shelf melting, which is a negative mass balance for the ice sheet. Then you have increased snowfall, which can partially offset it. And then you have this melt on the ice shelves, which reduces the capacity of the ice shelves or increases their fragility. So have any of you in these model outputs looked at connections between these different processes? So for example, where you have atmospheric conditions that lead to intrusion of CDW, does that correspond with increased surface melt or increased accumulation? And similarly, Michelle, you showed that where you have increased the high snowfall events, there's often warming associated with that as well. So is there any chance that you also have melt events that would coincide now or in the future? So I guess my general question is if there's any connections between these different processes that you each described, and if you've looked into that. Because you all knew ahead of time who else was in your session, right?
Yeah, so my research is ongoing, and I think the next phase I really want to look at is the sunlight angular mode and changes in the onwards and sea low over time, because that will play a big role in the precipitation that we see on slates. So that's definitely something I'm looking into.
I think the linkage here is these are all models sorry, I should correct myself. They're models and then also models that are sort of constrained by observations. And I think that's the big challenge right now. I think Michelle, you mentioned that, we don't have we just don't have measurements of this. And so we have to completely live in this model space where we have so much faith in these models, and they're fantastic and they do such an amazing job. It's sometimes hard to believe it. But at the end of the day, it's so much trust in models, and you can't really measure snowfall from space. I mean, it's a really big challenge, and I think that's sort of what I would say is just this sort of need for observations of these in these very inaccessible places, and where they get a lot of snowfall, which makes it even more complicated to try to measure. So I don't know. I guess that's sort of how I see they all link together. And then obviously what Gemma does of saying, hey, we don't even have great observations, let's use all these neat proxies elsewhere to reconstruct it is awesome.
Well, I think we're just about out of time, but maybe one final question for each of you in this vein is there one set of in situ or spaceborne observations that would really help answer the questions that you're asking, to put you each on the spot?
I sat too.
Drop the mic.
Bye. Yeah, I mean, I think as I just mentioned, you can't. I mean, we have CloudSat. We have some ways to try to measure snowfall from space, but it's still just quite the challenge. And trying to, I think what we're getting to now is we start to have all these different. We can measure snowfall rate. We can now with ISAT2 we can measure height change. We can measure all of these different components that don't necessarily give you exactly what you want, but maybe in conjunction with one another, you can start to back out these things that are the numbers that you actually want to understand. Like ISAT2 will give you a height change, but that doesn't necessarily tell you about accumulation. But if you can start to combine it with snowfall rates and ground observations and airborne observations,
and
then
CryosAT2 and CryosAT2.
Well, yeah.
You put those two together, you might be able to get snowfall from space.
Yeah. I mean, you might. Yeah. I'll trust you, Ted. So yeah, that's. I mean, and as I said already, just measurements. I mean, as many measurements as we can, so we can start, especially time series. You know, it's one thing to say, here's the mean accumulation rate here, and that's good, but it's like if we have a time series, so we can actually, because as Michelle showed, the interrandom variability is so strong, we can't pull out trends unless we have more time, basically. So.
Well, I agree with Brooke, and I wouldn't say anything else up here. Yeah, but again, just measurements of snow would be great. Right now, all we have to compare to each other are different models, and the representation of snowfall over thwaites mainly depends on the resolution of the model itself due to the slope of the glacier. So measurements would be very helpful.
So my reconstructions, I was sort of disappointed to see that the ice cores didn't have more influence in producing reliable reconstructions. So I would really love some coastal ice cores in the Amundsen sector to strengthen those Amundsen reconstructions.
Did Peter
Can I ask a
pay her to
question
say
about
that?
it? Is that just because of the locations of the ice cores, that they're not in these areas that actually represent sort of the zonal winds? So it's really not necessarily that the cores aren't good, it's just we don't have them in the right places. Is that okay?
I want them in places where there's a strong relationship between temperature, because that's what the ice cores mostly sense, and winds in Amundsen Sea.
Okay, great. I think there's some good messages there for observationalists and program managers in the audience. So, we've used up all our time, so we're going to move on to the next session. So let's thank our panel one more time.